Welcome to AP Calculus. Drum roll, please. This is the last video lesson for the regular course. Now, I may be putting some more videos out as part of our review, but this is our last section we're going to cover. And some of this would just be review from the previous sections of Section 8.3, but we will be talking about cylindrical shell method. There's some really good visualization tools for that available on the internet. You can check with me if you haven't found those, but Google is your friend. Okay, let's get started. Find the volume of a solid generated by revolving the region bounded by, we got to make certain that we're bounding these, we're getting the correct regions. Y equals square root of x, and the line y equals 2 and x equals 0. Quit cheating yourself with small graphs. Okay, so we're going to rotate about the x-axis, so I need to leave some room down below for what my graph looks like. So let's build our graph. We need square root of x. We've got y equals 2. We've got x equals 0. So if y equals 2, to get to 2, I need to put 4 in for x. And we know that graph pretty well by now. Looks like this. So we are bound by this curve. We're also bound by y equals 2, and we're bound by x equals 0. So we are dealing with this area. Okay, so now we're going to rotate that about the x-axis, which means we're going to end up down here, and as this rotates around, we've got a gap in here, therefore this is a washer problem. So I like starting this out as area of the washer equals area of the big circle minus area of the little circle, or pi, since they're circles, pi times big R squared minus pi times little r squared. And that is just a way for me to help organize my thoughts, maybe also for the viewer to get an idea what I'm doing. Okay, so now, what is my big radius? My big radius is this rotation right here, but that's constant all the time. It's the rotation of this line y equals 2, so that big radius is 2. So I get area in terms of x is pi times 2 squared 4 minus pi times, let's see, how about the radius of my little circle of rotation? That's this. It varies. And that is square root of x. So that would be square root of x squared x. And this is definitely a dx problem, because what we're doing is we're rotating, we're creating big circles like this, are actually washers as we go on, but all of those circles we're creating from 0 to 4. So we need integral. I'm going to factor out pi. I've got 4 minus x dx. And at that point, I'm going to take the liberty of leaving that for the viewer to go ahead and finish up. We can certainly go through that analytics. Okay, good news. Well, good news, bad news if this was a test. Good news is if we got this correct, we've got almost half of our work done for the next couple of problems. But if we have this image bound in the wrong region, we're going to miss them all. We've got to be really careful with that. So about the y-axis, I'm just going to start with a fresh drawing here. So my region was in here. And now we're going to rotate that this way. And my rotation now, there isn't a gap in it like when I went around the x-axis. So this can just simply be a disk problem rather than a washer. So my area of my circles that I'm creating as I go circle here, circle here, circle here, circle here, as I go from 0 to 2, we see this is a dy problem. My area of those is pi r squared. My r is this distance. That's an x, but we need dy. We need this in terms of y. And I've got y equals square root of x, but this is an x distance, so x is y squared. So area in terms of y is pi times y squared squared. So we get, oh, by the way, let me jump back up here. I bet you saw this. Here we were going from 0 to 4 x's. So now we're going to go from 0 to 2, the y's, factor out the pi. I've got y to the 4th dy, and once again, by this stage, if we're not able to get out of this, we got more problems than worrying about disks. Okay, a little twist on this. Around the line y equals 2. So let's get a drawing of this guy. If this is 2, same curve up in here. Here we are to 4. But now we're going to revolve this around 2. We're going to end up with this. And here's where you'll be able to show, does this make sense to us, this process, or am I just memorizing things? Okay. As this rotation occurs, I don't have a gap in here. This is just a bunch of circles we're putting together. And this is clearly a dx problem. So the area of these circles, the area of the circles is pi r squared. But what is the radius? Okay, our radius is from here to here. However, what do I call that? Well, I could get this by going, I could get from here to here by going from here down to there and then back up to there, which would be a radius of length 2, take away that root x. Radius is 2, take away the root x. Anywhere on here. From here, my radius, right there, can be found by starting with 2 and subtracting that square root of x. And then we let calculus do the work for us from 0 to 4. So I get my area in terms of x is pi times 2 minus square root of x. Oh, I got it up here. All right. So we need pi times integral 0 to 4. Area is, this is my radius squared, 2 minus square root of x squared dx. I'll take that one step further. Pi times integral 0 to 4. Let's see, I would get a 4 when I square this. I would get minus 2 root x's and minus 2 more root x's, minus 4x to the 1/2, and I would get a plus x dx. And once again, I'm going to leave that to the reader. Okay, line x equals 4. So here we're 2, here we're 4. This is just a regular old region. Lies in here. But now we're going to rotate that around x equals 4, so we're going to end up with this. And now I can invade that rotation. So this is a washer problem. I'm going to be taking circles. As I rotate this, I get this circle. I get circles with holes in it, but we're definitely a dy problem now. We're getting all of these rotations stacking from 0 up to 2. Okay, so this is a washer problem. Area of my washer equals area of the big circle minus area of the little circle equals, this is going to be a little bit sneakier, equals pi big R squared minus pi little r squared. What is my radius in terms of y? Well, my radius of the big rotation is simple. It's just 4. Always 4. So my radius is here, area in terms of y, is pi times 16, 4 squared, minus pi times. Now, this radius, the radius of the rotation along this curve, I could get there by saying it's 4 minus that distance. That distance is an x distance, but as we mentioned earlier, x equals y squared. So this would be 4 take away y squared squared. So we have integral, our y's run from 0 to 2. We've got pi, we've got 16 minus 4 minus y squared squared dy. One more step, then I'll leave it to the reader. 0 to 2, let's see. I get a 16. Here I'm going to get a minus 16 when I FOIL. Well, that's good news. I'm going to get minus 4y squareds and minus 4 more y squareds for a total of minus 8y squareds, but I need the opposite of that, 8y squareds. I'm going to get a plus y to the 4th, but the opposite of that, minus y to the 4th, dy, dot, dot, dot. You can wrap that one up. Make certain when you give these answers, though, we are dealing in volumes here. We're going to give the answers as something like units cubed or cubic units. Okay. Use the cylindrical shell method. Now, cylindrical shell method. I've shown this in class, and like I said earlier at the beginning of this video, there are some real nice things. If you would just Google calculus cylindrical shells, visualize, you're going to find some really cool visualizations of this. But here's how this works. We've got some volume, and in that volume, what we can do, you can kind of think of it as, let's just say we just have some kind of mound here, try to give this some kind of dimension. We've got some mound here, and what we could do to figure out the volume of this is we could just take shells, kind of like bullet cartridge shells, and stack those one inside of the other. So it's not shells like seashells. We're stacking those shells inside of each other. I know this isn't a great representation, not a great artist with this, but we're stacking those and we're finding the volumes of all of those things, putting those together. So we need to talk about each of those shells. So one of those shells, any one of those shells may look like this. And each of these shells has a volume. Now again, they're hollowed out because we're going to nest another one right inside of there, and our goal is to get as many shells with as small a wall casing as we can to represent the object. If we were to take this and slice this open and roll it out, it got really big, sorry, we would end up with just a rectangular prism where this distance would be 2 pi r, and whatever the height is here is the height there, but this right here would be my casing, and that is our dx. And that's where we let calculus do the work for us. We want that dx to get smaller and smaller and smaller until theoretically we have infinity of these shells just stacked together, and they could make up the volume of any figure we wanted. Okay, so let's take a look at what we're doing there. Oh, let me come back to this for a second. So our volume of this shell would be 2 pi r times h times dx. And you're going to find that r, unless we're revolving around something other than axis, you're going to find that this very good chance this is just going to become x for us. But you'll see what we're doing with that. So this 2 pi r h dx is a real player for us. That's going to be individual volume, then we're going to add the volumes of all of those shell casings together. Okay, use the cylindrical shell method to find the volume of the solids generated by the region bound by the curves about the y-axis. Okay, so we're going to go about the y-axis. We have curves. We're only going to x equals 2. Y equals x would look like this. It does tell us that we're solid generated by revolving the region about the curves about the y-axis. So this would go up to 2. This would go down to just -1. And we've got the line x equals 2. So everything is in the first quadrant, well, to the right of the y-axis, I should say. So we are taking this, and we're going to rotate that over around into here. Terrible straight line there. And as we're doing that, here's what we want to think about. We're taking these little casings and we're rotating that around into here. And we've got this little casing going on for us. And we're going to find all of those. So those casings, here's what's kind of different about this. Those casings are just a continuation along the x-axis. This is actually a dx problem when we're rotating around the y. The advantage of that is we don't have to convert our functions into x equals. In this case, this would not be a difficult washer problem whatsoever. It's an invasion. Here, we definitely have a washer, and we can dy this. But we're going to go ahead and dx this with cylindrical shell methods. There are definitely times when we need to use cylindrical shells when the other is very inconvenient to try to do a washer type problem. Okay, so here's what we've got, and this is for understanding. Hopefully, we need the volume of this, and the volume of this, the volume in terms of x is. Remember when we rolled this thing out, we get the circumference 2 times pi times r, but my r, my radius of this thing, is my x value as it goes from 0 to 2. It's x, then it's an x, then it's an x, then it's an x. So that is x, 2 pi r. The height of these guys is top function minus bottom function. X minus, that's my top function, minus my bottom function. X minus negative, x plus, x on 2. So there's, if I roll this all out again, quick review of what we just looked at, the volume of this is circumference times height times dx. And now we just need all of them from 0 to 2. So I get integral 0 to 2. I'm going to factor out the 2 pi. Let's see, I've got an x times 3 halves x's, so I get 3 halves x squared dx. 1.5 x times another x, 1.5 x squared. You could pull this out and make this, let's see, 2 cancels. I get 3 pi times integral 0 to x squared dx dot dot dot. Make sure you answer cubic units. This is a volume. Okay, hope that made sense to you. Let's take a look at B. Oh, here's a function that we were just looking at recently. Square root of x, when x is 4, y is going to be 2. So we're out to 4, we're up to 2. We're between the graph y equals 0. Y equals 0 is right here. We're between x equals 4, and we're between here. So similar function, before we were above, now we're inside of here. And we're rotating this. Again, I want to stress, these are problems that could be done with washers. But there are some times when washers are inconvenient. Okay, now because this is a rotation, this would be a washer problem, but we're not going to treat it that way. So here's what we've got. We've got this rotating around to here. Okay, so you can kind of envision what's going on there with our rotations. So our volume of each of those shells is the circumference, 2 times pi times r, but r is going to be this, then this, and this, as we just keep marching down, getting new shells. It's going to be x. We've got top function minus bottom function. Here's the good news. The bottom function is 0. The top function, so the height of this is just square root of x. and the width of these is dx. So what do we need? We need integral 0 to 4. We can pull out a 2 pi. I've got x times x to the 1/2, x to the 3/2 dx dot in cubic units. Okay, shells, very, very useful for us. Some people may choose to, unless you're directed one way or the other, you get a problem like this, you could use washers if you want, but you may choose to use shells on a problem. The big payoff on these in some cases is that I don't have to be able to solve for y to rotate horizontally. I can leave my functions as in terms of x. Why does that matter? Let's consider for a moment, let's say we had y equals negative x squared plus 3x. In this case, we would have a 0 at 0, we have a 0 at 3, and we know this is an upside down parabola, so this looks something like here. Now imagine if we were rotating that around and we get this look. If I was going to do this thing as washers, I would have a radius here for my small radius. I'd have a big radius there, but they're off the same function. We would need to solve this equation. We need to turn those x's into y's. We need to solve this for y. Take a moment and think about solving this equation for x, so we can get it in terms of y. We'd probably need to complete the square on this, and we'd end up with a plus or minus version of this. We'd have to treat this as the negative version, this is the positive version. That would be quite a mess compared to our shell method that we just looked at. There's a look at your last official book assignment. It's not review. We will have review assignments. And you will certainly be using the shell method on your test. Good luck.